Imagine being able to stop each color of light in its tracks: red, orange, yellow, green, blue, and violet, all frozen at different points along a tiny device. That is the essence of the photonic crystal rainbow trap, a technology that sounds like science fiction, but is rooted in real physics. It raises a simple yet profound question. Can we truly control light so precisely that we stop different colors in different places? To understand how this works, let's first consider what light is. Light is a wave made of electric and magnetic fields, and different colors correspond to different wavelengths. Blue light has shorter wavelengths and more energy. Red light has longer wavelengths and less energy. When you shine white light through a prism, it spreads out into a rainbow because each wavelength bends differently, a process called dispersion. Now imagine taking that idea a step further. Instead of simply bending light, what if you could build a material that traps each color, literally stopping it at a specific location? This is the principle behind the rainbow trap. It uses photonic crystals, which are materials with nanoscale patterns that repeat over distances comparable to the wavelength of light. These patterns can create a photonic band gap, which acts like an optical fence that blocks certain wavelengths from moving forward. By gradually changing the structure of the photonic crystal along its length, making the pattern tighter or looser, you create a situation where each color of light runs out of road at a different point. The crystal essentially slows down each wavelength and brings it to a halt at a unique location. It's like designing a road where smaller cars stop on the steep hills first, while the larger ones roll farther down before stopping. This concept has practical uses that go far beyond curiosity. One key application is in optical sensing. By stopping light of different colors at different points, you can build extremely precise detectors that recognize tiny changes in color, chemical composition, or temperature. Another application is in solar energy. If light can be held in place longer, it increases the chances of being absorbed and turned into electricity. In quantum technology, controlling how and where light stops could help synchronize delicate quantum operations, allowing for better communication between quantum bits, qubits. Has anyone built a rainbow trap? Yes, on a small scale. Researchers have created structures out of silicon and other semiconductors that slow down light dramatically. In some laboratory setups, light has been slowed to a crawl thousands of times slower than in air, using photonic crystal designs. These demonstrations show that the concept works, although challenges remain. For example, light can scatter unpredictably or get absorbed by the material before it reaches its stop point. Also, fabricating these nanostructures requires advanced techniques and exceptional precision. The rainbow trap is a vivid example of how engineers and physicists are learning to sculpt the behavior of light with astonishing accuracy. Instead of letting light pass freely, we are beginning to shape its path, delay its journey, or even bring it to a halt, one color at a time. Photonic crystals are periodic dielectric structures that affect the motion of photons, much like a crystal lattice affects electrons. Their periodicity leads to photonic band gaps, ranges of light frequencies that cannot propagate through the material. By tailoring the periodicity and refractive index contrast, photonic crystals can manipulate light's speed, direction, and confinement. This makes them useful for controlling dispersion and localizing light of specific frequencies. Their design enables a high level of control over electromagnetic wave propagation in optical devices. A one-dimensional photonic crystal can block specific wavelengths from transmitting, much like a Bragg reflector, like a musical instrument with tuned resonators that allow only certain notes to pass through or be amplified. The rainbow trap refers to a device that can spatially separate and localize different wavelengths of light across a gradient structure. As light enters a tapered photonic crystal or metamaterial with gradually changing properties, each wavelength slows down and eventually stops at a specific point. This happens due to the matching of the light's group velocity to the local band structure. Shorter wavelengths penetrate further while longer wavelengths stop earlier, forming a spatially ordered rainbow of trapped light. The energy of each color is confined at different depths or regions of the material. A tapered photonic crystal waveguide can trap blue light deeper and red light closer to the surface, like raindrops landing at different distances from a sprinkler, depending on their size and momentum. Dispersion describes how different wavelengths of light travel at different speeds in a material. In photonic crystals, the dispersion can be engineered by adjusting lattice spacing, material composition, or geometry. By creating a gradual change in dispersion along a structure, it's possible to slow light down progressively, eventually reducing its group velocity to zero. Each wavelength becomes trapped at the point where the local dispersion curve flattens. This is the mechanism underlying spatial separation and halting of different frequencies. A chirped photonic crystal structure alters the periodic spacing to tune the dispersion in trap specific colors. Like tuning piano strings to vibrate at specific points, each note finds its perfect stopping spot. The slow light regime occurs when the group velocity of light becomes very small due to flat photonic band structures. As light slows down, its interaction time with the material increases, enhancing absorption, nonlinearity, or sensing sensitivity. In a rainbow trap, this slowing continues until the group velocity reaches zero at a specific point. At that location, light is effectively halted, and its energy is stored momentarily in the material. This enables highly localized optical field enhancement. In a waveguide with gradually decreasing width, light slows down and compresses until it stops at the narrowest point. Like a car driving into deeper sand, it gradually slows and finally gets stuck at a depth based on its speed. Creating a rainbow trap requires precise material control and gradient design in the refractive index, or periodicity. Materials must have low absorption at the wavelengths of interest to avoid loss during trapping. Additionally, fabrication resolution must be high to create gradual and smooth transitions over nanoscale distances. Structural asymmetry, or chirping non-uniform periodicity, is key to spatially differentiating wavelength. Such conditions are typically achieved in silicon photonics or advanced metamaterials. Silicon insulator waveguides with engineered nanohole arrays are used to realize wavelength-selective trapping, like a slide with bumps, sized to catch different sized balls at different positions. The rainbow trapping effect can be exploited for solar energy harvesting by maximizing absorption over a wide spectral range. By spatially separating and slowing down light, the photon residence time is increased, enhancing interaction with absorbing materials. This can boost the efficiency of thin-film solar cells or photodetectors. Trapped light can also be coupled into resonators or nonlinear materials for frequency conversion. Such applications aim to concentrate energy where it is most effectively used. Trapped blue light in a photonic trap enhances energy conversion in UV-sensitive photovoltaic layers, like holding each color of sunlight in its own energy jar. Each one optimized for maximum benefit. Trapping and delaying specific wavelengths could aid quantum and optical information processing by acting as buffers, delay lines, or spectral filters. Controlled halting of photons allows synchronization of signals, storage of quantum states, or enhancement of nonlinear effects. Spatial separation also enables multiplexing of signals in photonic circuits. The challenge lies in minimizing dispersion loss and decoherence during halting. Rainbow traps could serve as wavelength-sensitive memory elements in future optical computing architectures. A rainbow trap slows down light pulses of different colors for timing alignment in integrated optical chips, like placing runners of different speeds on staggered tracks to ensure they finish together. Rainbow traps have been demonstrated in laboratory conditions using graded photonic crystals, metamaterials, and nanowave guides. However, maintaining low loss, high spatial resolution, and precise control over dispersion remains difficult. Material absorption, fabrication imperfections, and modal dispersion can reduce the effectiveness of trapping, additionally ensuring reversible control, i.e., releasing the trapped light, adds complexity. Nevertheless, experimental progress continues toward practical on-chip rainbow traps. Researchers used a chirped metamaterial slab to trap visible light components at different depths under a microscope, like catching different colored marbles rolling down a hill in separate boxes set at just the right heights. The rainbow trap inverts the function of a prism, not by refracting light into directions, but by arresting each wavelength in space. It represents a fusion of dispersion engineering, nanophotonics, and metamaterial design. As research advances, these devices may become key tools in sensing, energy harvesting, and optical information control. By freezing light spatially rather than temporally, rainbow traps offer a new paradigm in manipulating photons. It shows how understanding wave behavior enables us to reimagine even the basic act of color separation. A photonic crystal waveguide that halts green, red, and blue light at staggered positions functions like a prism that immobilizes the spectrum, Like stopping every note of a rainbow-colored piano at a different key. The music never plays, but all the tones are held in place.